NASA Connect asks us to show you the student activity for this program.
When you think of the Earth or Mars orbiting a planet, you might think that the orbit is in the shape of a circle. It's really in the shape of a square circle or an ellipse. The German mathematician and astronomer Johannes Kepler discovered this fact a long time ago. In this activity, you'll use measurement and observation to understand the meaning of the eccentricity of an ellipse. You'll calculate the distance between Earth and Mars, determine the lengths of their orbits, and learn about their orbital rates as compared to their distances from the Sun. But before we get started, here are the materials you'll need. A computer with a spreadsheet program or calculators, centimeter graph paper, 2 push pins for each group, a string 25 centimeters long for each group, cardboard, and 1 metric ruler for each group. Kepler stated that the orbit of Mars or of any planet is an ellipse with the Sun at one focus. The other focus is an imaginary point. There is nothing there. During part of its orbit around the Sun, Mars is closer to the Sun than it is at other times. This relationship can be seen in solar system data charts that show the maximum and minimum distances from the Sun to each planet. Astronomers often use the average or mean distance from the Sun instead of the minimum or maximum. Enter the data from the chart into a spreadsheet program or use a calculator, and for each planet, find the mean distance from the Sun. Now make a sketch of the orbits of the Earth and Mars around the Sun. Another column of data on the planet chart lists the eccentricity of each planet's orbit. Eccentricity gives an indication of the roundness or squashness of each ellipse. To understand what this number means, here's an experiment to do with your team. On a piece of centimeter graph paper, draw 2 lines, one near the middle vertically and one near the middle horizontally. The lines intersect at the center point. Measure and cut a piece of string about 25 centimeters long. Tie a knot near the ends of the string to form a loop. Place the graph paper on a piece of cardboard. Then place 2 push pins along the horizontal line, each 1 centimeter from the center point. These pins represent the foci. At this point, the foci are 2 centimeters apart. Loop the string around the push pins, then use a pencil to keep the string tight and draw an ellipse. Measure in centimeters the length of the ellipse along its major axis. Record the distance between the 2 foci and the length of the major axis on a chart. Then divide the distance between the foci by the length of the major axis and record the quotient on the chart. Now repeat these steps using the following distances between foci: 3 centimeters, 4 centimeters, 5 centimeters. Choose your own distance. After you have recorded the distances between the foci and the length of the major axis on the data chart, use a calculator to divide the distance by the major axis length. The quotient will give you the eccentricity for the ellipses. Remember, the value of the eccentricity should be a decimal with a value of less than 1. On the chart, make sketches of the ellipses you've created.
Analyze your data, guys. This would be a great time to stop the video and consider the following questions. How does the distance between the foci affect the shape of the ellipse? What is the relationship between the value of the eccentricity and the roundness or squashedness of the ellipse? Although the orbits of both Earth and Mars are ellipses, these orbits are close enough to being circles that we can estimate the distance from the Earth to Mars. Let's assume both planets are on the same side of the Sun. Consider the mean distance from the Sun to each planet as the radius of a circle. Use the mean distance you calculated from the Sun to Earth and the Sun to Mars to determine the estimated direct distance between the Earth and Mars. What if Earth and Mars were on opposite sides of the Sun, like this? These activities and more are located in the Educator's Lesson Guide, which can be downloaded from our NASA Connect website.